So this video is really about practicing strong acids and strong bases. What do the problems look like? How can we solve these problems? So the first skill to master here is actually being able to identify the strong acids and the strong bases. And that's really just recollecting what you learned in Gen Ed chemistry. Then we're going to relate the concentration of H plus to OH minus and to pH. Also, we're going to have to relate pH to pOH. So there's just a few basic equations that you can use to solve any strong acid or strong base problems. We're going to do one example of each. Okay, so starting, what is the pH of 0.5 molar hydrochloric acid? So we're given what the acid is, and of course this is strong acids and bases, so we know that hydrochloric acid, HCl, is strong. And then what else are we given? We have to find the pH. We're also given a concentration of the amount of hydrochloric acid. And so we can assume that this and all of the strong acid and strong bases equations are going to be done in water. Okay, so what this reaction is really going to look like is HCl in water is going to dissociate completely, so we don't need the reversible arrows here, to H plus, Cl minus, and it's still going to be in water. So looking at this equation of everything that's going on, the water on both sides can cancel. Now we have the equation HCl plus, goes straight to H plus and Cl minus. Okay, so now we should set up an ice chart. It's just a good practice to get into. We know the initial concentration, so the I stands for initial, C stands for change, E stands for equilibrium, and you plug in concentrations or moles as long as all of your units are the same. So the initial concentration of HCl here is 0.35 molar. Then we're adding it into water and it will dissociate into its ions because it's a strong acid. So the initial concentration of H plus is 0, the initial concentration of Cl minus is 0, because this is the moment before this hits the water. The change, because this is a strong acid, and the same is true for strong bases, is that 100% of this is going to become this. So we're going to lose 0.35 molars of this, gain 0.35 molar H plus, gain 0.35 molar Cl minus. Okay, now we do the math. 0.35 minus 0.35 is 0. This is gaining 0.35 molar, and Cl minus is also gaining 0.35 molar. So now we have the equilibrium conditions for this problem. Okay, so the next step is to remember the formula pH equals the opposite log of the concentration of H plus. At this point, this is the concentration of H plus in solution. So we just plug in negative log of 0.35 molar. So I'm going to show you what this looks like in your calculator. Clear this. Okay, so you type in 0.35 in your scientific calculator, hit log. So this is the log of 0.35. So it's 0.456 because we add one extra significant digit for logs. So we're going to take the opposite of this log, negative 0.456, and when you distribute this, we end up with positive 0.456. And that is the final answer. pH does not have units, FYI. So this is the answer. Okay, similarly, what is the pH of 0.35 molar sodium hydroxide? Formula for this, sodium hydroxide. Okay, and again, we're given a concentration. Difference here, this is not an acid. This is a base. It is a hydroxide donor. This does not have H plus to donate. Okay, So this is going to be a slightly different problem, but we can answer it following the same sort of steps. So as we saw before, strong acids and strong bases, when they combine with water, completely disassociate into their ions, and the water on both sides cancels, so I'm skipping that step. Now we can make our ice chart, which is a good habit even though you don't technically need it for strong acid or strong base problems. Again, starting with 0.35 molar sodium hydroxide. We start with nothing of the products. Those haven't been made. The change, 100% of this, is going to be made into products. 0.35 plus 0.35. And this gives our equilibrium amount of 0 sodium hydroxide, and everything is sodium ions and hydroxide ions. Okay. So now we've got a slightly different problem because we know pH equals the opposite log of the concentration of H+. What we have here is OH-. So what we can do is solve for the POH, which is the opposite log of the concentration of OH-. Okay, but how is this going to get us to pH? You must remember that pH plus POH equals that magic number 14. So what this is really saying is to solve for the pH, we're going to have to take 14 minus the POH. And so if we spell that out by plugging in this formula for POH here, so 14 will be minus the opposite log of the concentration of OH, or 14 plus the log of OH. Because you can't minus a negative, you can make both of those pluses. Okay, so this is what we're going to do. So we know the concentration of OH is right there. So we can solve for pH equals 14 plus the log of 0.35. Lucky us, we already know the log of 0.35 after we plugged it into our calculator is negative 0.456. So this means that all we have to do is subtract, clear, 14 minus 0.456. 13.544 is the answer here. 13.544. And now we're running into some trouble with significant digits because in addition and subtraction you have to go with the number of significant digits of the least. And so that's going to actually give us the same answer because as we round up, the pH is basically 14. The real answer, well, for what a lot of biochemists would do in this situation, you could say 13.5 off to the side. But in significant digits, it's 14. Okay, that's it.